So our next speaker is Roberto Fernandez, prime.
Okay, so now what I would like to discuss now is the time of truth. Okay, is really the convergence criteria. This is what set statistical mechanics people apart from more algebraic-minded applications. So let me review briefly the setup. So I have a countable family of objects that you can, let's call it them polymers, they go under other names. You can think them as vertex of some graph. There is an incompatibility constraint, which you can think as being just neighbors in the graph. Okay? So two neighbors are the same as being incompatible, and there are some activities that are given by the application. And you construct the partition function, which is this long sum, where, okay, this combinatorial that I discussed, where there is the product of the activities, and the only thing that mixes a little bit, which involves pairs of polymers, is the compatibility constraint.
Excuse me.
Yeah.
Can I ask you, do you have any reason to put here is the product of all these weights? Just here, J gamma 1, J gamma 2, up to J gamma n.
Yes.
If you put some other function, is okay?
Well, the point is that you can put anything that is a function of a single polymer.
Okay, so here,
That's
just
all.
a special case you consider product.
No, I mean, this is a very general function of a polymer. I'm saying.
No, but he wants something other than a product.
Yes.
I think the answer is you
No.
want a product because as long as the polymers are compatible, they were supposed to be independent.
Yeah, no. So in this approach, it's only products. The only thing that is non-product is this. Okay, the only thing I allow in what I'm discussing now. If you can put things that, of course, there are treatments with situations in which there are more than just product there, but this falls outside the scope of what I'm going to discuss, the new results that we have.
Roberto, there's a question here.
If
Sorry.
if you could think of the activities as weights
Yes?
on the edges of this graph. The graph
The weights are associated to the vertices in this case.
to the vertices.
Yeah.
This is the independence polynomial that Jason Brown was discussing yesterday. Well, these are because compatibility of a group of polymers simply in the graph theoretic language means that it's an independent set of vertices.
Yeah, they are farther, they are not neighbors.
Right. So this is a multivariate version of Jason Brown's independent set.
You mean
independent set
this
polynomial.
expression, the xi? I was just wondering this expression that you have this xi of zeta. What would it be in this case? I mean, what
In which case? In the case
if you put those weights
on the edges.
if you think completely graph.
So then there will be another term here besides this. There will be some function of the whole edges of the pair, vi, vj.
No, I think he's asking, you don't want weights on the edges. You have weights on the vertices, right?
Never mind.
No, he wants.
What does this mean? Could this xi of z have some?
This is precisely
They depend.
This is precisely the multivariate generating polynomial for independent sets of vertices. You could simply write it as sum over all independent sets of vertices in the graph and product of the vertex weights for the vertices in the independent set.
But there would be nothing preventing you from putting weights or variables on the edges too.
There'd be nothing preventing you, but Roberto doesn't want to do it.
Yeah, I don't want. I certainly don't want it.
When you write gamma 1 up to gamma n, actually consider all, you take the order, right? If you
Yeah, this is
take the order,
ordered.
it get different. If you don't write that such a way, you can remove the n factorial.
Yes, exactly. Here, yes, but when you pass to the log, watch out.
You just consider one say you remove the n factorial.
Yeah, and here, yes.
But there is a complete theory of interacting polymers.
Yeah, except that our results don't apply. That's why I don't want to insist,
And he
because
doesn't want to make
the
it
new
harder
and
than needed.
Yeah, here the only interaction is the last term.
exactly, and that's the one that applies to the chromatic polynomial too. So I
for the
stop there.
So for the combinatorialist, I think Feng Ming is right. The definition of this thing can be written more simply as simply sum over independent sets and then a monomial for each independent set. The reason Roberto writes it in this slightly more complicated way is that the logarithm of that independent set polynomial will not merely be multi-affine. The logarithm will have terms z gamma 1 squared, z gamma 2 to the 17th. And therefore, he wants to write it in this way so that he can write the logarithm in a similar way.
So the one actually is corresponding to the second set.
Today?
One, the first term one.
Yes.
Actually is for the independent set. For the empty
Empty
set.
set. Empty set is
Exactly
one.
the one.
Yeah.
Exactly.
Okay.
Okay. So you introduce the cluster expansion, which is the log of the partition function, or what you put inside an exponential. And the clusters are, these coefficients are the Ursel functions, and the clusters are the families for which this is not zero. And of course, and you see the similarity in the way of writing, but here, watch out, you cannot just replace this, omit this if you put braces here. I mean, it's tough to put braces there. Okay, so let's keep it this way. Okay, so now, what is the classical way to, I'm going to compare three ways of proving of getting convergence criteria, okay? The initial way, the inductive way, and our way. Okay. No, but the idea, because I think that the point is not just the convergence criteria per se, but the ideas that go in these proofs. I mean, I don't know. Maybe they are already present in some other fields, or they may be useful in other fields. Okay, so we put absolute values, and this is our object, which corresponds to somehow the series you obtain for the derivative of the log. But with absolute values there. Okay, and what you want is, well, this is what, once you prove that this series converges, which is a series of positive terms, so the only thing you have to prove is that it's finite, then you get all you want.
And TCL is an acronym for central limit theorem.
Yeah, that's in a
You've
Latin
been teaching too
angle.
many French.
It's in Latin. It's in Latin. Yeah. Okay. So now is the time to give you the expression for these truncated functions, which I didn't want to do in the first time. So you take your polymers and you construct a graph defined by the polymers, which is the graph on the set of indexes 1 to n. The vertices are 1 to n, so this is even a third graph in the game. And the edges are the indices that correspond to incompatible or neighbors polymers. Okay? And the expression is in terms of this graph. So if you have only one polymer, there is 1. If the graph is not connected, then it doesn't contribute. And if the graph is connected, you get this expression that has already been mentioned at some point yesterday, I think. Okay, you take all the subgraphs of this graph that are connected and spanning, and you put a factor -1 for each edge of the graph. Okay, so that's the expression. This is an algebraic identity when you take log as the level of formal power series, and as you can see, so this is well known, not trivial but well known, and once you know how to prove it, it's not difficult. But you see that if you want to estimate this is one of these nightmarish formulas, because you have a large number of cancellations there, and you have to deal with it in a very efficient manner. If you put absolute value right there, then you are doomed.
So -1 actually is the special case of the weight, right? -1 can be replaced by the weight of every edge in the new graph defined here.
Well, let me see.
Yes,
Probably yes, but
if he had done the generalization where instead of polymers interacting purely by an exclusion,
yeah,
he had polymers interacting by a repulsive interaction, then this -1 would be replaced by some weight between -1 and 0.
yeah, but you cannot accommodate more than just edge weights. The multi-edge, multi-hypergraph, these things that do not fit. But anyway, I'm particularly interested in the case -1. You will see the -1 is important. Okay, now how do you deal with this expression? And there is something that has been neglected for a long time among statistical mechanicists, which is this Penrose identity, which is in fact the efficient way to get it as an identity. And he realized that to deal with these cancellations, you have to do something that now is understood correspond to what is known as partitionability of a family of connected spanning subgraphs. This I learned from Alan. Okay, and
I learned it from Creel Marino.
Okay. Okay, so I'm going to prove this theorem in the next transparency, but for the time being, let me show you what it tells you. You take a graph, and you wanted to do exactly the same sum that you were interested. Now, there is a family of trees, particular family of trees that are connected and spanning within the graph. Okay, this G has to be the same G there, which let's call it Penrose, such that you have this identity. It's just -1 to the number of vertices -1 times the number of trees of this family. Okay? So you see the alternating sign feature explicitly, and you have an identity of the size. Okay? Now, what is this partitionability of subgraphs?
Rick, just make one other comment. Just go back for a second to see how incredibly useful this lemma is. Imagine the underlying graph G were the complete graph on n vertices. Then the number of terms in the first sum is of order 2 to the n choose 2. Because there are 2 to the n choose 2 subgraphs of Kn, and they're almost all connected. So you have, if you were to put absolute values, you would have a disaster. You would have 2 to the n choose 2, which is the disaster Roberto was talking about. It's super exponential in n. But you get this enormous cancellation, and in the end, you're bounding it by Penrose trees, which is bounded above by all trees, which is merely n to the n minus 2, or n factorial.
Looks a bit
You meant
like
2 to the 2 to the n
combinatorial
minus 2 to the n.
construction.
I'm sorry.
2 to the n choose 2. Every edge is present direction.
Sorry. Let me take it. I forgot to.
Yeah, right. Point is, you're eventually going to have an exponential generating function with these coefficients, so you'll have a 1 over n factorial. If you had 2 to the n choose 2, that would grow too fast. You would have 0 radius of convergence.
Yeah, this has a 1 over n factorial preceding it in the cluster expansion. Okay, so let me prove this identity. It's a part of a particular case of a more general identity that I call it Penrose identity anyway. The idea is the following. You take a connected graph, finite. You consider all the spanning subgraphs and all the trees that are spanning subgraphs. Okay? And you order this family of connected spanning subgraphs by number of bonds. Not by number, by bonds, by family of bonds. You say that a graph is less or equal than another graph if it has less bonds. So it strictly contains the set of bonds. And you define an interval as all the graphs whose bonds are in between. Okay? Now, a partition scheme for this family of connected spanning subgraphs is a map that starts from the trees. To each tree, it associates another graph, which is bigger, so it has more bounds. It's obtained by adding some bounds. It's obtained by adding some bounds, and it has to have the property that you can partition the family of subgraphs into intervals that go from 3 to its corresponding R of tau. Okay? So this allows, so the whole CG is a union of this over all taus, all possible taus, in principle. Okay. Now, Penrose gave a particular way, and this is important for us, the way Penrose defined this partition, but there are others which have not been exploited. This is some homework to do. So how do you do it? You have the vertices of G, you order them in some way, doesn't matter, it's a finite family, and then you can define the tree distance from any vertex to the first one, to the root, you think as a rooted tree. So for every tree, what you do is you add all the bonds that are in your initial graph and not in the tree you've taken that satisfy the following. Either they are between points of the same generation, or if there are connecting points with a previous generator, but they correspond to a smaller index. Okay, so for us, the first one is going to be important. Okay, so if you have a tree and some of the children of the same vertex are neighbors in the original graph, you add this bond. Okay? Well, this gives you a partition scheme. And the idea is you consider the trees which cannot be completed anymore. Okay? So that no, you cannot add any more bound, or they don't have the possibility of adding the bounds according to the previous prescription. So in particular, for instance, children of the same vertex are always incompatible between themselves, because if they were compatible, are compatible between themselves, okay, or they are not neighbors. Otherwise, you would add this bond. And the proposition is that this sum is -1 by -1 times the number of trees in this partition scheme. Okay, this is the general result, of which Penrose is a particular case because he used a particular partition. Now, how do you prove this? It's one line, 2 lines. Okay, let's put xe instead of -1. We are interested in -1, but it's clearer if you see it with xe. So you are interested in this sum. You sum over all spanning subgraphs, and you multiply all the bonds of the subgraph, the weight for the bond. So you classify them according to these particular trees. You multiply the bonds in the tree, and then you complete this tree with all possible ways of adding bonds up to the end of the interval that is defined. Okay? And then you observe that this sum here, by the identity that I mentioned in the previous hour, read it from right to left, is just the product of 1 plus xe over all the bonds in the x that are in the largest graph R of tau, but not in tau. Okay? So if you are able to add, if R of tau is strictly bigger than A of tau, here you have a factor 1 plus xe at least, and if xe is -1, this is 0. End of it. Okay? And then the other factor -1 to the v -1 comes from the fact that the number of trees, of bonds of a tree is v -1. That's the proof. In a sense, it's very elementary. It's extremely powerful. Now, and this is the discussion. This explains why my obsession with -1. If x is not -1, the only thing I could say is, well, this difference is less or equal than 1 in the repulsive case. And then I cannot go beyond the usual bound that people have used, is replacing this by just the sum over all the trees, the number of trees. Yes?
Do we have any categorization of the family of the spanning tree?
Categorization of what? Of the TR?
Yeah, it means this special family of spanning tree.
Yeah, well, it depends on how your partition is defined. These are trees that satisfy this constraint.
Or
that
you can find, how can we find such a family?
Well, there are many prescriptions.
So the point is, this identity is valid for any so-called partition scheme. Penrose gave a particular partition scheme, but there are others. For example, you can order the edges and define the partition scheme in terms of the lexicographic ordering of successive edges. So there are various partition schemes, and each one will give a different definition of which trees satisfy R of tau equals tau. And in principle, any one of these could be useful. It's not.
Yes.
It's a non-canonical thing.
I'd like to add too that the one that you just mentioned, lexicographic order based on edge ordering, is precisely Tutt's recipe in general activity.
Right.
And the general identity that you mentioned, I think it's the Möbius function for partitions in general, I think.
It is a Möbius function of, not the partition lattice, but you only take partitions such that each block of the partition, the induced subgraph connects that block.
Well, I mean, the point is, there is inclusion-exclusion in this game, except that it's not been proven that way. Maybe Milos, will you speak about relation? Okay. There is another comment that the point are the number of triangle diagrams. If you have it's easier to do Penrose trees if you have a smaller number of triangle diagrams. So the number of Penrose trees grows the smaller the triangle diagrams. So that means that trees, I mean things that do not have triangle diagrams, are the worst case for the convergence because they have the biggest size of Cn.
So you say if the underlying graph G is itself a tree.
Yeah,
That's kind of the worst
that's
case.
the worst case. Okay, now the classical way you measurize the series is you just use the tree graph bound. You forget the fact that here you have some particular trees. You say, okay, I take all the trees, all the spanning trees. Okay, so the expression we wanted to measurize, which was this sum 1 over n factorial, the sum over contours, so we can written like this. Now you sum over all the trees inside this graph, okay, between 0 to n, where 0 is going to be thought as the root. Okay, and other than that, you don't have anything. This is rho gamma 1, gamma n. Okay, so you can interchange the sums, and so eventually you end up, see, this summing over trees. You can think rooted trees, and then summing over all possible configuration, all possible choices of polymers or of vertices, such that the tree is contained into the graph that you would obtain from them. Okay. That gives you this sum there. So, and this is a notation for all the trees of vertices 0, 1, n rooted in 0. Now, the traditional way to get convergence is you have to sum, so you have to sum over all trees. Okay? You have to sum over all trees there.
Roberto,
Yeah.
maybe you could emphasize that here there is a transport of structure because you had a tree where the vertices were polymers. Now your vertices are just an abstract set of labels.
Yeah, and so there is the third level of graphs. That's why I avoid graphs if possible. Yeah, this is a trees on a graph. On this graph is not on polymers, but on the indexes, 0, 1, up to n. Okay, but it's determined by the initial polymers because the links are between indices that correspond to polymers that were incompatible in the first place.
Can you explain this with the T-bars of tau?
Let me see. Is T bar so tau? So this, you understood what is T bar to n is the sum when you fix n and you sum over gammas. So then I invert this order of sum, and I put the sum over trees before, and then the sum over gammas that realize these trees. Okay, and so everything that you sum, I call it T bar sub tau. Okay, so the traditional way is you have to sum over all trees these weights. So the traditional way is you start from the leaves of the tree, and you defoliate the trees, and you come down. Okay, so for instance, look to the real leaves. That means that you have, so the notation I'm using, suppose that gamma I is the father of all these leaves. Okay, so I'm using this is I, and then you have the leaves that I'm denoting IG, where G, this is I1, I2, up to I, some SI, number of children. Okay, this is the notation I'm using to simplify. So you have to sum over all possible ways of putting gammas in these leaves, these SI leaves. Well, this is, you have, the only constraint is that these gammas have to be incompatible. That means neighbors of gamma I. So you get a factor like this. Now, if in the geometric case, which was the traditional case, there is an intersection, incompatibility is related to the intersection, so you just bound it by the number of sides in this gamma I and the sum of the gammas that touch this side. It's an upper bound, but it works. And then, so then what happens is that the ancestor that had a weight gamma I get a weight gamma I SI on top, and the leaves keeps this factor. Each leaf has a factor sum over rho gamma. So now you iterate. You have to sum over the gamma i's, which are themselves children of another. So now you have to do a similar sum, but you are going to pick up a factor gamma I to this I. So if you iterate, eventually you end up with a sum of this type. Okay? So n is the number of vertices, well, n plus 1 is the number of vertices. So in each vertex, you have to sum rho gamma times gamma to the si, where si is the number of children such a vertex has. The leaves, there won't be any. And then you see that this expression only depends on the s's. So when you are going to sum over all trees, this will break into a sum over s's and multiply by the number of trees with the given s's, which is Cayley theorem, okay? Which gives you that. So you insert this there, and you are going to pick up an n factorial for the first outside, and then s factorials in the bottom, when there is a 1 that you have to that you forget. So you end up with this expression. And this gives you an exponential. Okay? So you see that in order to have convergence, this sum has to be less than 1. And that's the initial criterion that it took a long while to write it in this way, the proof. The proof was much more difficult at the very beginning. It's a long history.
You might remark that a combinatorialist might think it more natural, instead of doing this sum over trees level by level by level and using Cayley's counting, you could equivalently write an exponential generating function for the sum over trees, and then you get a recursion which says simply the sum over the whole tree equals the root times the sum over all the.
But that's exactly what we did.
Of things on the children.
That's what we did.
You're going to do
That's
that.
what we did.
Yeah.
Somehow. And that's what I'm afraid. I mean, we are rediscovering things that were well known. But I don't know by whom. Yeah, but that's exactly what we did.
Roberto,
Yep.
this argument, where did it first appear? Do you know?
Let's see. I mean, it's the argument as such is ascribed to Camarota. And given that there is an Italian in the audience, I cannot say otherwise.
Camarota in which?
82. Because before that, I mean, there were, I don't know who was the first, but there is a book by Seiler on gauge models, lattice gauge models that have a different proof that was the historic proof. It's much more difficult to follow. But Camarota he found the trees, the tree argument.
So this argument with the Cayley.
Yeah, it started in Camarota.
Export.
There is a nice version, there is this Bridges note, Les Souches notes, which was a classical reference for my generation, say. Okay, now the Kotesky prize came into the game. And they did something very nice. They did two things. One, they produced a different approach, inductive, as I mentioned last time. And second, the condition got a little softer. So instead of asking that the exponential be less than 1, you have to find some function of the, this is not g, it's backslash g. So this is gamma prime, a of gamma prime and a of gamma. So that when you sum the exponential, you fall back into the function. Okay? So that was the new type of criterion. And then Dobrushin came along. Every 10 years there is another, okay? It's, let me see, no, even less than that. When is, Dobrushin was 94, Kotesky prize was 84. Yeah, so more or less 10 years to Dobrushin came that. You had a question?
Just the first one is the G prime the derivative of G?
No, it's G prime is
be
backslash
gamma
G prime. Should be gamma prime. I forgot the backslash in
Gamma.
tech. It's gamma prime here and gamma there. So this you sum over all the gamma primes that are inconsistent or neighbors of a given gamma. And you put this exponential weight, e of gamma prime, plus the weight that it has. And all this sum has to be less or equal than the exponent for the weight of gamma. Okay? But then Dobrushin came with another condition, which is not immediately comparable in this way, but I'm going to show you a way in which it is immediately comparable, which is a better condition. And just to show you the spirit of the proofs, because part of the message I want to pass to you is the ideas that were here were playing a role. Let me tell you how you could use this condition to actually do the thing in inductive approach. I mean, just the very basic thing. What Dobrushin did is to exploit something that should be like deletion contraction in some sense. You say the sum over all possible polymers in lambda is the sum this partition function in which you exclude one polymer plus the partition in which this polymer is present. Okay, so this here is all the polymers that are consistent with gamma 0. Otherwise, they couldn't be there. Okay, so you start with this identity. Okay, and the theorem it proves is assuming this condition, then you get that. Okay, in particular, this shows that this ratio is finite, and this ratio is what we were after in the first place. So the log of this ratio is finite. Okay, notice that if you a consequence of this by telescoping, you can go from lambda to any lambda prime container and just sum the a's, corresponding a's. Right? Okay, now how do you prove this idea? You start with this deletion contraction, you put absolute values, and you get this. Okay, well, and then you use precisely this condition here, which is the.
What was the star?
The star was this identity. I'm going to do it by induction in lambda. Okay, so you start with this identity,
So
which relates lambda with
in
something.
combinatorial language, you're saying the independent set polynomial for a graph lambda is, you consider one vertex gamma naught in lambda, and you say either that vertex is occupied by an atom, I mean, does belong to your independent set or doesn't. If it doesn't, then you have an independent set in lambda minus gamma naught. If it does, then you get the weight for gamma naught, and the rest must be an independent set in lambda, delete gamma naught, delete all the neighbors of gamma naught. So that symbol means delete the extended neighborhood of gamma naught.
Okay. Okay, so I have this. So if you divide this deletion contraction identity by C lambda minus lambda naught, and you put absolute value, then the first is a 1, then the row is, because upper bound for z, small z, and then you have this thing. Now, if you use this expression, you see that here you have the difference that involves the neighbors of gamma 0. Okay, so you can use it and you get exactly this. Okay, because the log was bounded by the sum, so you get that. And the condition 1 that Dobrushin imposed, the condition of the theorem, is exactly what you need to guarantee that this thing gives you the exponential again. And that's the end. Okay, there are a little bit of inequalities then because there are some values here and there, but that's it. I mean, it's extremely elegant. Very, very nice. But the question is why it works. Okay, now, one of the steps that helped us a lot is to put the thing in a nice comparable way, the two conditions, Kotevsky price and Dobrushin. For this, you have to do a substitution. I wrote it here. And then you see that Kotevsky price can be written in this way. You have convergence for a given row if this row satisfies this inequality. For Dobrushin, you replace this second function by this function here. Okay? Which is certainly an improvement because in the Dobrushin function, you only consider monomials of mu. And here you have powers, all type of powers. Okay? So that's what I'm saying there. And in fact, Dobrushin gives the exact answer for polymers that have only self-exclusion. Now, if you see these two things, it looks as if there were a hierarchy of approximation, and Dobrushin was extracting more information out of the problem. Which information? And the second question is why this form? Rho times a function less or equal than mu. So that's the kind of questions we started discussing during a long year with Aldo. And then somehow what came during the discussion is two things. First, if we have to prove improvements, it has to come through a better consideration of the Penrose identity. It was an identity after all. And the second, this suggests iteration. That's what Alan said. Okay? So this is our new condition, and then I'm going to show you the idea of the proof. The new condition is the following. You fix for each gamma 0, you take all the polymers that are incompatible with it, all the neighbors in the graph, in the interaction graphs, and you do the partition function of them. So you sum over all possible combinations. Of course, here they have to be compatible. So you take all the polymers that are incompatible with a given polymer, but in here you take all the families that are compatible between themselves. Okay?
So again, this is just the independent set polynomial for the extended neighborhood of gamma naught.
Gamma naught, yes.
And if you go back to your previous, go back one more. There. Or
One more.
the left-hand side there is sum over all subsets of vertices in the extended neighborhood. So this improves it by looking at only the independent ones.
Okay. And then you consider this, and the condition is exactly the same as before, but we replace this phi that was exponential or the product by this partition function. Okay. So that's what I say. And well, okay, this is you know it better than I do. So let me summarize. All of these conditions now are of this form, except that you get progressively better and better functions phi. Okay. A little bit of proof here, advertisement. How much do you improve this way? And just to be honest, I start by the side in which we are not the best. So we take maximal degree, and that's the only information you use from the graph. Okay, and then Koteski price is inferior to Dobruchin, which is inferior to us, but Scott-Sokal still beat us. Okay, they have a better argument, which only works for trees, in fact. Now, for the complete graph, we get the best, because we get exactly the radius of convergence. You see, you gain, in our approach, the gain comes through the triangle diagrams. If the original graph has triangle diagrams, then there are many things that are forbidden in our function phi. Okay, so if you take the complete graph, which is you have the maximum diagrams, you get the complete improvement, and in fact you get the right answer. Okay, for instance, we did it for degree 6, and you can see how the improvement goes. Now, if you take particular, for instance, domino system, triangular lattice, or the complete graph, we can use this information and improve it. The previous approaches cannot. They don't consider the triangle diagram. Okay, and if you go back to the geometrical polymers, we obtain this condition. In fact, let me compare this. This is the condition that Koteski price had. This is Dobruchin. Our condition takes the best of both worlds. Okay, take the Koteski on the left, but the exponential except for the one on the right. Okay, now, to our surprise, and in fact, we were very happy because that was also one of the motivations. We were not the first to arrive to this expression. This was already present in the initial paper on polymer expansions, Gruber and Kuntz. But they did it in a more obscure way using Kirchhoff-Salzburg equations, and people forgot that. So they kept using Koteski price, and it was there all the time. And now for chromatic polynomials, but I will discuss a little bit how you obtain this. Our improvement is not dramatic, but there is some improvement. I'm comparing with Sokal did, and this is the change for the infinite limit. I mean, for arbitrary large, from 7.9 to 6.9. For the complete graph, we get a little better, but far from the right answer. Okay, so I'd like to discuss a little bit the ideas of the proof. So probably these ideas have been there in the market, it's just that we didn't know. So the first ingredient is to use Penrose. And to use Penrose, you remember there were two properties in these Penrose partition schemes. We are going to use the first one only. The fact that if you consider a tree a Penrose tree, then children of the same father or mother have to be compatible. Because if they are not, that means in the original graph there was a link, and when you apply this map that defines the partition, you have to add this link, and this won't be one of these trees that is left invariant under the map. Okay? So we keep only this constraint, and then this amounts to mapping, instead of by summing of the Penrose tree, by summing over all the trees that have this constraint, that can be written in this way. The constraint is just a constraint on each vertex of the tree, that all the children in this vertex have to be compatible among themselves. Okay? And this is what put us in the right track, and this would allow us to do what Alan was proposing. Because this is a property of the vertices of the trees. Okay? In fact, here is the right expression. Okay? In here, everybody has to be incompatible with the first, but they have to be compatible between themselves. The first is something that is a little bit outside. Okay? The weights here do not involve the first. So now, once you got to this, we saw that there was a recursive approach. Okay? And the recursive approach is in here. You see, we have to sum over all possible trees. So let's start with the first generation trees. First generation tree is this function, the function t, which is rho of the root, and then you sum. Either you don't put anything, that's the 1, or you sum 1 to n up to any n trees of one generation with the mu that is the argument, imposing the constraint that everybody here has to be compatible. So the 1 and 2 have to be compatible between themselves and incompatible with gamma 0, and the same here. Okay? Now, what happens if you repeat this? Namely, you put as mu t rho of mu. Then you would obtain second generation trees following the same prescription that we're interested. And then you iterate. Okay? So this is, so you replace each of the dots, the black dots, by first generation trees, you get the second. You continue, and eventually, in the limit, you recover the series you were after. Okay? But there is an alternative way of seeing the thing. If I want to get the full series over all the series, what I have to do is to replace each of these dots by the series itself. Okay? So this is my alternative. I could replace rho by the series, which I'm calling rho star. So I get this relation. So that was the idea. Now, you have to guarantee that the series converges. What is the cheapest way to guarantee it? Well, you use monotonicity. If you can find that there is a mu such that t rho of mu is less than mu, t rho is a series of positive terms, so it respects monotonicity. When you apply t rho to both sides, you obtain t rho squared that is less or equal than t rho that is less or equal than mu. So you obtain that the whole sequence t rho n that will converge to rho star is bounded above by mu, so it has to be finite. End of it. It's a very cheap way to do it. Okay? But in fact, it's more than that. I mean, of course, if there is convergence, this is satisfied with mu equal to rho star. So it's an if and only if condition. So here is our theorem. Okay? You get the convergence if you have this condition, where phi is this function that involves only the first generation trees. Okay? And within this relation of convergence, you have, well, convergence like this. You have this relation that I just wrote, and let me point out that this means that if rho star, this long series, you think is as a function of rho, this formula is telling you what is the formula for the inverse function. And moreover, you have this sequence of bounds that tell you that if you really want to bound rho pi for some reason, then mu is an upper bound, but you can obtain better and better upper bounds just by iterating this transformation. So that's the idea. Okay. Now, if you apply for our criterion, our Cn is just this product. Everybody has to be compatible with the root, and it has to be compatible between themselves. So this first generation tree function is rho gamma 0, and all the sums in which you ask all of these to have these both constraints. And this is exactly what we call the the restricted partition function of the neighborhood. Okay? So if we ask that this be less or equal than mu, the series will converge. Now, what did Dobrushin and Kotesky price, what do they correspond to? Well, Dobrushin, you replace the condition of being incompatible by the condition of being different, which is a weaker condition. Okay? So you do exactly the same, and you recover the Dobrushin function. And if you forget anything whatsoever about relation between the gammas, and you only put the incompatibility with the root, you get Kotesky price. So now we recover the hierarchy. And this method of the iteration also can be thought as a summing from the roots up instead of from the leaves down. Okay. Let me, just to get a feeling, and also because it will be useful to go back to chromatic polynomial, consider what is called here the univariate case. Okay. So everybody equal to z, z gamma equal to z. So there is no more gamma dependence. It's the same for every gamma. So now the product of rho gamma is just a factor rho n, and then I have some number there. And the phi, the one that will enter into the criterion, also has numbers that only involves first generation trees. Okay, here you have overall possible trees, here's just first generation. Okay, then our theorem tells the radius of convergence of such a series is this supremum. And in fact, that's the way we used to compute the things in the table, the improvements that I showed you. Okay? Let me do even a simpler case to see that it's something that was known. Take only one polymer. Okay? So the only thing you can have is just copies of this polymer, so you don't say it, you just, these are numbers, C of Si. So then you have a relation between these two objects. This is the first generation, and this is the sum of overall trees. Let me do the simplest possible case, Cn equal 1. So the series we are talking about is this series, and the function phi mu, if Cn is equal to 1, is just exponential of mu. So the theorem tells us that the radius of convergence of this series is the supremum of mu e to the minus mu, which is e to the minus 1, as it should. And moreover, if this series, I call it C, is f of x, then it satisfies this relation. C is x e of c. This is rho star is equal to rho times phi of rho star for us before. Or if you want, c over e of c is the inverse function of this function. Or if you want, you have this. This is well known by people you can find it in books in graph theory. I mean, this is what Borg used to Borg-size your formula. Okay, so somehow we're getting a generalization that maybe was well known, I don't know, from things well known from the univariate case. So to finish, let me see what all tells us for the case of chromatic polynomials. Okay, so let me remind you, in the case of chromatic polynomials, you have to consider cluster expansion, which is a geometric cluster expansion. The clusters are just sets of vertices, and the weight is this one. So as it is a geometrical cluster expansion, we have to use the criteria for the geometrical convergence, which for Kotesky price with this sum less than a, and for our or Gruber-Kunz, this sum less than e to the a minus 1. So now you have to put it back into the condition here. So if the size of the polymer is n, this you get an e to the a n, and then you have to sum over all the gammas that have size n. If you do that, the convergence condition becomes one of these two, where here you are taking the supremum or all the sum of all the activities for all polymers that has size n. Okay? And now, at this point, our approach can give two sources of improvement. One is, of course, that would not be ours, that would be Gruber-Kunz, is to use this instead of Kotesky price. But there is a second source of improvement, that in Z gamma, there was already the expression that for which Penrose identity is tailored. So we can get a better estimation of Cn using Penrose identity.
You do it
Twice.
So you're using the Penrose identity at two different levels.
Yep.
You use it at the level of this graph whose vertices are polymers and whose edges are incompatibility, in order to sum the cluster expansion.
Mm-hmm.
And then you use it again in this application at the level of the original underlying graph in order to control the weights Z gamma in
Exactly.
the cluster expansion.
Exactly. So
But the second use will not give you better bounds in terms of maximum degree.
no,
Give you better bounds if you know more about the
exactly,
underlying graph.
exactly. Yeah. What I'm saying, it corresponds to the best. So the improvement on Cn is to consider the number of Penrose trees for the graph with a given root and taking supremum over the graph. This is worse, a little worse if you forget this and you get all the trees. That's how the Sokal and Scott Sokal things have been done. And there is even a further down that is a further bound, which will correspond to forgetting everything about the degree, and is just counting the number of possible trees. Okay? So let me explore the three things, because we have a little time. So if you look into the conditions, then the zeros are, you get that the cluster expansion converges, and therefore you don't have zeros when the number of colors, or the absolute value of Q, because Q could be complex here, satisfy this inequality. Okay, you have minimum over A. This is the A that comes from the criteria. This kappa is the 1 over Q that happens in the partition, in the fugacity, in the Z's, and it has to be less or equal. It depends on which you use. Okay, there is an extra complication here because you want to start from power 0, and then if you, in the original thing, started from power 1, so you are adding a 1 to both sides, basically. Okay, so let me not go in detail, but that's basically the expression to look at, this thing here. Okay, where you have to do good counting for Tn, and you can, in principle, you should use the best one. Now, if you call x this e to the a over kappa, then you get an e to the a outside, the mean goes into sup, and then the f of x has this expression, and then there is a -1 because the kappa is in the denominator. Okay? So let me look at this instead, where the expression is here, and for this Tn, we can put any of the three things I said before, either the number of Penrose trees, the number of trees, or this bound in terms of n to the n. So if you start with the worst, what we recover is this f that I just discussed, that was known in graph theory, okay, the sum over n to the n minus 1 divided n factorial, that we know that divided by x is e to the fx. So the condition we're after, suppose that you use the Kotevsky price bound, big F less than that is e to the little f, so little f is less than the log. But as we get, we know the inverse of f is c over e to the minus c. And then, well, you just do that, and you get this expression. There is an inversion because remember that in order to pass to sup.
Where does maximum degree come in here?
No, there is no maximum degree because.
Well, there has to be some maximum degree.
Well, in this bound it disappears. This is the limit that you get when delta goes to infinity.
Yeah,
It's the constant proportional to delta.
Yeah, the delta, that's what I mean. The delta can't disappear. You're supposed to get this thing multiplied by delta. Some kind of a delta to the, maybe there's a delta to the n?
Bo.
No.
But the expression, the final expression is this one.
Well, no, it can't
This
be
is correct.
because you don't get the bound
You're
q
not-
greater than or equal to just some number. It's q greater or equal to some number times delta.
You use data in the continuous number of trees, many trees.
Yeah, go back a few slides. I think
maybe
there's
I'm-
some deltas that
Yeah.
are missing.
Let me see, where is the delta there?
Go back more. Go back there.
There is the delta.
Here, there is a
Yeah.
Is there a delta to
Yes.
To
the
the,
n?
Yeah.
delta to the m.
Yeah.
T n
Yeah.
are the
Okay.
number of what?
This is the number of trees that are subgraphs of G, subtrees of G. And this is, well, okay. I'll look it up. For the transparency, I will correct it then. But the expression is this one. Let me see. Yeah.
It must be,
Q over delta.
somehow you're counting.
Q over delta. I think I'm forgetting the delta in the Q. Q of delta. Q over delta, yes. Yeah, there is a Q over delta missing somewhere. Okay. This number is the 7.97. Yeah, there is a delta missing in here. This Q over delta here. This is 0.97. If you replace the Koteski price by the Gruber-Kunz, you get the 691. Okay. Now, if you go to find a maximal degree, then you write big F as this in this way, and then this is the number of trees of delta trees included touching a fixed vertex. So delta is the maximum degree of your graph. So anywhere in the graph, you take the root, it has delta choices at worst. Now, how do you construct this series? You can do it in the same way we did it. Okay, you can say, okay, to construct this series, I start with x, choose some branches out of the delta, and for the branches I choose, I put the trees again. Okay, so you get this relation. Okay, which well, immediately you get this expression. So you can prove this through our theorem, but it's more elementary than that.
This is overcounting?
This is overcounting, and I'm going to come to this because I want to do it slowly because this is the part that some people confuse. Okay, so, well, if I continue, okay, so my condition is this. I replace by f, little f less than this because big F was f over x, which is 1 plus to the 1 over to the delta. And then I use the inverse that I said, and that's the expression you get. Now this is overcounting because after you choose the root, for the root has delta choices, but all the other points have delta minus 1 because they cannot choose the predecessor. So what you have to use is instead this relation, that f delta is x, but what you put inside, once you have chosen which of the first children, which of the branches, delta branches are going to be your first children, you have to put delta minus 1. So if you do that, you obtain an improved thing, which I believe this would give you your table. And of course, you can improve it already with by replacing this Koteski price bound by the Gruber-Kunz bound. Now, you can use Penrose trees. Let me go fast. And the point is that how do you use? You have to use the fact that you exclude triangle diagrams. Okay? So each root, the root can link to any neighbor, and other vertices can link to neighbors except the predecessor. So what you have to check is difficult to write. I mean, so you have to consider, given a vertex, all the possible families of k vertices for each k, such that they are neighbors to the root, but they are not neighbors between themselves in the original graph. Okay. And this is for the choices for the root, and the t tilde is when you exclude one of the vertices because it's the predecessor, could be the predecessor. Then this combination will play the same role as 1 plus x over delta in the previous argument, and the combination with 1 less plays the role of this. Okay, and then I'm forgetting the over delta throughout. You get no, the over delta here, yeah, the over delta is also. You get this general expression that is it's much more complicated to evolve, but in principle could give an extra improvement. Okay, so that's the story. The question is how many of these ideas have been circulating in other fields, and they are so elementary in some sense, so natural once you arrive to them, that I'm sure that they have been used before. And I think that that's kind of the beginning. I mean, there is much more to be obtained from this idea of iterative schemes. Okay, I stop here. Yes.
So where do you see further progress on what kind of ideas you think?
Well, let's see. I've got some list, but we have incorporated only part of the constraint. There was an identity there. We have not exploited other partition schemes other than the Penrose that could be more suited to some problems. We don't know. Of course, there remains the idea, the question whether you can reprove it inductively. What happens if you consider soft interaction? Aldo has done something about this, but there is some discussion to do. Well, I'm interested in quantum contours. This idea circulating here on hypergraphs, things like that, it could be another direction. Okay, this is the immediate things we see. Yeah. Okay, but I hope that by discussing with people, the other things will come out. This is
Maybe just to add about this thing about hypergraphs, so that you can all know what Bill and I are trying to do, but haven't yet succeeded in doing, so you can do it first. That you remember this bound on the roots of the chromatic polynomial in terms of maximum degree is unnatural, because the chromatic polynomial factorizes over blocks, so you can have a cut vertex with a huge degree, and nevertheless the chromatic roots are just the union of the chromatic roots of the blocks. The maximum degree is unnatural, and we think we know what the right quantity is. It's this max flow, and somehow the natural way to exploit that would be to go back to, remember when Roberto gave you the polymer representation for the chromatic polynomial by taking the Fortuyn-Castellane representation, and then he said the polymers were the connected components other than isolated vertices of this Fortuyn-Castellane subgraph. Instead of saying connected components, what if you say two connected components? That might be the natural thing to do. But then what constraints do you get? And that's where Bill's question to Roberto in his first talk was going at. Then the two connected components are allowed to overlap in one vertex, but not in more than one vertex. And then as Svante realized, but you get further constraints because if you allow three polymers, they're allowed to mutually intersect in one vertex each, but they're not supposed to form a cycle and more things. So in addition to two polymer constraints, you get multi-polymer constraints. So your polymer graph is not a graph, but a hypergraph. You have to redo all of this cluster expansion stuff for hypergraphs.
and there will be a Penrose
and
hyper.
kind of put it all together.
You
And
need-
maybe it will get you a bound on chromatic roots in terms of the max flow of the original graph.
You need a hyper Penrose identity.
Well, or maybe, no, you can just maybe do without the hyper, I mean, you don't have to use this Penrose identity.
No, but it helps a lot if you use it.
But
Another direction would be to exploit better the partial sums, not to put the absolute values where you put them and use some cancellations before putting absolute values. Okay, that's probably Milos will say something about it.
Just make a remark about this. The second item is important in this, trying to pursue this objective, make some resummation, to find something different from the Penrose partition schemes that help to see this resummation that could improve a lot the convergent values of cluster expansion. Because there is a minus sign that we missed. There is there. Also in the Penrose identity, there is a -1 times the number of Penrose trees that we are missing. Could be utilized to perform this resummation.
yeah, another way of saying that is back in those variables Z, you were looking simply for polydiscs in Z where the partition function is guaranteed to be non-vanishing. And so you're looking in all directions in complex space equally and finding the root closest to the origin, which happens to lie on the negative real axis in all of those fugacities because of the alternating sign of the weights. But you don't have to look for polydiscs. You can look for any regions you want and try to prove that the partition function is non-vanishing in them. And indeed, these zero-free regions tend to extend much farther in the positive direction than in the negative direction. If you had some way of not just taking absolute value everywhere, but working harder with those complex numbers z. Maybe you could get better regions.
Time to have lunch. Okay.